you can hear me, right? Okay, cool. I will start talking. So I'll just stand here so that I won't disturb you from watching the slides, and also I'm a bit nervous. Yeah, so today I'll present the spatial temporal prediction of soil and carbon density for Europe from 2000 to 2022 in 3D plus D and its uncertainty. It's a long name. I'll walk through every word of it in the yeah, so organic carbon density is important, as all the previous talks have already stated. Uh, our work is about providing a complete dynamic information about the organic carbon density over the whole Europe, and it's done by this general pipeline you see here. It's quite an ugly plot, but you don't need to focus too much on that. You just need to know there are several steps in this pipeline. I'll walk you through all the steps step by step in the following slides. Some features about this pipeline: modular, is updatable. So whenever you solve some issues, you spot some faulties in the pipeline, in the data products, you can just rerun the whole pipeline to get a new version, updated version of the data. It's generalizable. I use it in carbon densities map modeling and mapping, but you can also apply it to other environmental variables like I don't know, trees, plant covers, soil pH, other soil properties. And random forest, which is one of the I would say most simple but robust models, machine learning models, is also the core algorithm of our modeling and machine mapping pipeline. And this pipeline is not only about the predictions, but also about the uncertainties, the prediction uncertainties associated with the predictions. The first step is to prepare the input, the input to fit the model. One very important part is covariate, the features. And again, it's another ugly plot, but what's important is that we prepared time series of Landsat based satellite derived indices about vegetation, crop, soil exposure, and tillage. And they're all available at 30 meters resolution across the whole Europe. From 2000 to 2022, they're available at bi-monthly level and annual level and long-term aggregation. We use it as a cornerstone for the prediction of the soil and carbon density. And just to give you some idea of how it may look like, this is a tillage index, normalized tillage index. And you can see it's quite detailed. It aligns well with the cadastre data, the administrative data, and it's available as time series. Another major component of the input data is the soil organic carbon density measurement data. And they spent quite long time to just to collect all the data from different sources and harmonize them to be consistent. As you can see, it's just an idea like these are all the sources we collected the data from, and they are all measured by different. They're all about soil organic carbon content, but they are measured by different methods from different laboratories, from different years, and we have to make them consistent. We have to harmonize them to be comparable with Lucas, which is again the benchmark data set in this for this soil and carbon harmonized data. And the domain knowledge is a key here. That's where we really need the input of soil scientists. And so that's the current result of the harmonized soil and carbon density data. It covers the whole Europe. We're missing some data from Ukraine, Turkey, and Norway, and it basically covers the year from 2002 to 2020, and it's quite it's not a balanced or say normal distribution. It's quite inclined to the small soil and carbon density. And once we get both two components of the input of the soil and carbon density model, the data and the covariates, we can register them together, like to form regression metrics. So we extracted the corresponding environmental information from the same spatial location and the temporal period, and to form such a tabular data form. Like so, each row is a individual measurement, and each column stands for a different environmental feature. And this is done by a function developed in-house in an OpenGeoHub called scikit-map. And once we get this tabular data, we just feed them into the machine learning models, and the model gets trained so that the model can be scaled up to generate predictions. But before that, we need to make sure our model is reliable, or say is accurate. So we did 3 types of model evaluation here. The inverse sampling intensity weighted cross-validation. That's the first column you see. We do that because we do have a cluster soil and carbon density data, so we have to take that into consideration when evaluating it. And the second column is live 1 year out cross-validation. This is to assess the temporal consistency of the model. The last one is the holdout test data, holdout test validation, which is tested on a test data set that is held out from the whole training process. And we can see that the live 1 year out cross-validations metrics are the worst, while the holdout test metrics are the best. And in general, we think the model is reliable but less consistent throughout the time. That's kind of expected because most of the campaign, the soil campaign we used, they don't last more than 1 year. So when you do the live 1 year out cross validation, you actually leave one lab out, or so you leave one complete soil survey out. That creates this like it reduce the performance. And once we know that the model accuracy is okay, we also need to validate the model's performance on uncertainty estimation. I won't go to technical details here, but basically on the x-axis is the perfect uncertainty estimation. That's what we would like to achieve, and on the y-axis, that's what we achieve with our model, and they kinda align well. So now, after the prediction accuracy assessment and the uncertainty accuracy assessment, we know that our model is kind of reliable. We scale it up to make predictions on different space-time blocks. So we do this spatial temporal predictions in 3D+T, meaning it's not only longitude, latitude, like the X, Y, and also deeper into the soils from 0 centimeters to 2 meters, and across times from year 2000 to 2022. And for each space-time block, we predict we make 4 predictions at the corner of each space-time block, and then take the average as the block prediction. And that's the results. So on the top rows, you see the general maps of soil and carbon predictions. On the left is the upper bound of the uncertainty estimation. In the middle is the mean prediction. On the right side, you see on the right column, you see the lower bound of the uncertainty estimation. And the pattern kind of makes sense. And if we zoom into 2 points, A, B, and C, they're from peatland, woodland, and cropland. You can see the patterns here is that peatland has the highest soil density, which is not very surprising. And that's the spatial variation. And if we go deeper to look at the predictions in deeper soil, we see that of course, the soil and carbon density decreased across steps, and for peatlands, the uncertainty, the shade indicates the uncertainty predicted. The uncertainty is just consistently very high across the depths for the peatland soil, and for cropland soil and woodland soil, we get decreased uncertainty until 2 meters. Like when it's deeper than 1 meter and 2 meter interval, we get the uncertainty level just increased again. And we also try to see whether the temporal variation of the predicted soil density makes sense. And yeah, from 2000 to 2022, the temporal variation is very subtle. You cannot even tell from the series of figures I showed on the red panel. So that's the like qualitative check, visual check on the predicted maps. But apart from the prediction maps and the uncertainty maps, we also produce the extrapolation risk probability maps using a method called isolation forest. So this map basically tells you where is our model extrapolating. And the higher the score is, meaning the higher the chance that the model is extrapolating, is predicting on some unseen cases. And this map highlights the mountainous areas and snowy area and also Turkey. That's also expected because we have very limited soil samples from those areas. But if you compare this map with the data availability maps I showed earlier, you'll find that though we don't really have data from Ukraine, but the extrapolation probability is quite low there. Our guess is that this area, though we don't really have data from there, the general feature space is share some similarities with points from other parts of Europe. Yes, so after producing the map, like producing the maps is not the end, and our aim is to continuously updating when new data comes in or new issues are spotted. And here I borrowed a concept from software development. It's CI/CD, like continuously integration, continuous development. So it's more like a dynamic process. It's a loop. It's not just finish and done. It has its life. It should be continuously updated. And that's pretty much about the pipeline. We also did some other analysis. For example, it's again a lot of information on the plot, but the core message is that soil depths, vegetation, spatial aggregate all those pixel predictions to a regional level. The uncertainty actually reduces. That's because the low spatial correlation. And that's pretty much it. Here are the preprint paper, data, and code. They're all available, publicly available, and we welcome your visit to these links and check if you find something interesting or find some issues. Please let us know. And that's it. Yeah, and I need to advertise a little bit tomorrow afternoon in expert room 6 and 7. We'll go more details into the whole pipeline I presented here. The idea of that workshop is that you can learn how to do the whole thing yourself and you can apply it to your own cases. And thank you.